Number 10 on worksheet 7a. Here, when we do a direct substitution, thinking about what the graph of ln of x looks like, we realize that the x-intercept is 1, 0. So when we plug 1 in for ln of x, we get ln of 1 is 0. Plug in 1 into the exponent and we get 0 to 0 power, which is one of the caterpillar indeterminate forms. So what we're going to do is exponentiate and ln the expression, take the natural log of it, so that we can bring the exponent down and rewrite it as one of the familiar indeterminate forms 0 over 0 or infinity over infinity. So let's see where that takes us. So if we stick an ln in front and then exponentiate, our expression becomes e to the limit as x approaches 1 from the right of the ln of x, which is your base. We can bring the x minus 1 down as on the same level as the ln's. And so from here, if you do a direct substitution, you're going to get 0 times infinity. So think about that. This expression right here, 1 minus 1 is 0. So you have that's equal to 0. And then ln of, so this part right here, ln of 1 is 0, and it's from the right. So then you're looking at ln of what happens with the limit, what happens to the limit of ln of x as it approaches 0 from the right, means that it's going towards negative infinity. The y value is going towards negative infinity. So you have 0 times negative infinity, which is one of our indeterminate forms as well. Remember the Battle of the Giants. So then what we have to do is rewrite this so that it's a fraction. And the best way to do that is to move the x minus 1 down into the denominator. So in order to do that, we rewrite it as 1 over x minus 1. Now at this point, if you do the substitution again, you would get the top expression is still negative infinity, same as when we did our direct substitution earlier. Plugging a 1 into here, we have 1 over 0, or 1 over 1 millionth, which is equivalent to like a million. And so we have negative infinity over infinity. And so at this point, it's an indeterminate form that we recognize as one in which we can apply L'Hopital's rule. So limit as x approaches 1 from the right, take the derivative of the top, which would lead us to 1 over ln of x, times, that's the outside function, times the derivative of ln of x, which is 1 over x. And then the derivative of the 1 over x minus 1 separately would be negative 1 over x minus 1 squared. X minus 1 to the negative 1 power would result in that as the derivative. And so now simplify before you do a direct substitution. That's important to do because there's just too much going on. So that means I'm going to get rid of the fraction over fraction by keeping the top as 1 over x ln of x, but then multiplying by the reciprocal of the bottom. So if I flip that up, that's going to give me negative x minus 1 quantity squared over x ln of x. And when I plug 1 into that, I should get that I have 0 on top, and ln of 1 at the bottom is going to give me 0, so 0 over 0. So keep going with L'Hopital's rule. And I get the derivative of the top is negative 2 x minus 1 to the first power times the derivative of x minus 1, which is just 1, over, the bottom's going to require product rule. The derivative of x is just 1 ln of x, plus x over the derivative of ln of x, which is 1 over x. And so let's try our direct substitution now. If we, actually, let's go ahead and simplify this a little bit. E to the limit of x as x approaches 1 from the right of negative times x minus 1 all over ln of 1 plus 1. Well, if we plug the 1 into the top, we get 0. If we plug 1 into the bottom, we get, sorry, this was supposed to be x. I think I prematurely added the 1. So ln of 1 is 0. 0 plus 1 is 1. And we don't have a 0 at the bottom, so it's no longer indeterminate. I can conclude that that limit is equal to 0. And then finally, adding in the e to the 0 gives me that that limit is all equal to 1.